So, hello everyone, welcome back. Can people hear us okay online? Okay, I'll take that as a yes, and if anyone has any problems online, they can stick it in the chat and we'll sort it out. Okay, so for the first speaker of the afternoon, we have Ed Hartnett talking about NetCDF compression improvements. Oops. Okay, thank you.
Thank you. Hello, everyone. I'm Ed Hartnett. I'm delighted to be here to talk about NetCDF compression improvements. I work at NOAA, the National Oceanic and Atmospheric Administration in Washington, D.C., although I actually work in Colorado. And I previously worked at Unidata, the home of NetCDF. I would like to acknowledge some of my collaborators on this work, Charlie Zender from the University of California, Irvine, and Ward and Dennis from Unidata, and also Hang Lee, Brian Curtis, and Kyle Gerheiser from NOAA. And we all worked with the Unidata crew to bring some more compression features to NetCDF. And it's great to be addressing a group of scientists and engineers, and I can tell because everyone is seated the maximal distance away from everyone else. That's how you know you're talking to the real programmers. Okay, what is NetCDF? Anyone ever heard of NetCDF? Raise your hand. Okay, some people. NetCDF is a set of software libraries and machine-independent data formats that support the creation, access, and sharing of array-oriented data. NetCDF was there before HDF5, but not, I think, before HDF4. I can't remember. At the same time. And it's still going strong. NetCDF is completely interoperable with HDF5. Any HDF5 file can be opened and read by NetCDF and vice versa. So you can use NetCDF tools on your HDF5 data and vice versa. So it's good to know about. I added this up just this morning. 25 years ago, I was hired to work on NetCDF and combine it in some way with HDF5, a new format at the time. And it's been going great since that time. And I want all of the HDF5 people to be acknowledged for the systems that have been built on NetCDF4, which includes HDF5. And those include the Global Forecast System and NOAA right now, the NOAA Daily Weather Forecast. HDF5 is integral to that. All of the data is saved in HDF5. The Copernicus program, the ESA program. Anyone here from ESA? Raise your hand. Oh, talk to me later, guys, okay? You're going to the dinner tonight? I'm going to talk to you about your space program. They use NetCDF4 for all data. GOES-R, which is NOAA's flagship of the fleet, uses NetCDF4 for all data, and NASA uses it for many of its Earth science missions. And so all of those depend completely on HDF5, and those users are very interested in performance enhancements and new developments in HDF5, which we can then bring to them. And here's an example, zstandard compression. So zstandard as a filter has been available in HDF5 for a good long while now, and some of you may have used it. Recently, we have given it first-class treatment in NetCDF. I should mention that NetCDF now has full support for all HDF5 filters, but if you've worked with filters, you know that it can be a little complicated to figure out exactly how to set them and all. And with NetCDF users, we're talking about scientists mostly writing in Fortran, atmospheric scientists, not programmers, so we like to give them an easy way to do it. And we have given them functions, def-var zstandard and inc-var zstandard, so they can turn on zstandard compression on their data very easily. And one thing I just learned this morning was that the HDF5 plugin directory can now be set programmatically. Did I hear that? Wow. I should come to more of these conferences. My wife always tells me that. I'm gonna have to explain this to her, and she's gonna be telling me that again. Okay. Okay, so zstandard is something HDF community knows about, but here's something new. We have implemented something we call quantization in NetCDF. And what this is, well, when you're saving a 32-bit or a 64-bit floating point number, you're saving a certain amount of digits of precision, which is frequently much more than you need or want, right? But you just take it because 32-bit floating point is the smallest floating point size. And this puts a bunch of bits on the end of your numbers, which are basically random, and which you then compress and decompress every time you write the data. And why do that, right? So we have this feature where you can specify the number of significant digits of your quantity that you care about, and it will guarantee to keep enough bits for that precision, but the rest of the bits it rounds away. And when it does that, the compression happens a whole lot faster, and you end up with much smaller data. Let me see if I've said it all. Okay, it ignores fill values because fill values are for unwritten data, so those are ignored. It only works with floating point data, doesn't do anything for integer data. Here's an example with pi. At the top, you see pi expressed as a 32-bit floating point integer. It's got the sign, the exponent, and the significand. And as we go down, we have less and less significant digits. Number of significant digits is NSD. And you see the effect it has on the binary, on the significand, is having more and more zeros at the end. Until when you get down to only one significant digit, 3.1 is being shown, but only the 3 is guaranteed. Then you have almost all zeros. So you see the effect that this will have on your data. We have provided 3 different algorithms for doing this. We call them bitgroom, granular bit round, and bit round. And I'm not going to really go through them in detail. Well, I guess I will. Bitgroom is just alternates between setting extra bits to 0 and 1 so that it doesn't change the average of your data. The other 2 use IEEE rounding. IEEE defines a way to round floating point numbers, and it uses them on each number. The third one, bit round, was put into place because NOAA was already doing this manually, as it were, setting 14 bits or something to zeros. And they wanted to maintain that capability because they'd already checked that out in the science. And here's an example in C. So we define variables, and then here we have these 2 function calls, NCDF var quantize, and we're just turning quantization on for these 2 variables. So you do it variable by variable, and you set for each variable the number of significant digits that you want to keep. Okay, so back to the zstandard question. I've got some graphs here now. So here in these, we see lossless compression. And on the left is the write rate. So larger is better or faster. On the far left, you see the write rate with no compression at all. And then we use various compression technologies. zlib is, of course, the kind of standard. And as you can see, it has a very dramatic effect on the write rate. On the far right, we have zstandard. And as you can see, for producing the same amount of data or the same compression, it's nearly twice as fast as zlib. On the right side here, we have the resulting file sizes, and you can see that zlib reduces the file size quite a bit, zstandard the same amount, but twice as fast. So this is why we're recommending zstandard instead of zlib. Now, when we add in the quantization as well, zstandard performs even better. On the left, we have the write rate for the different, the same data, but with quantization used. You can see it's going a lot faster because it's writing less different bits, I guess, and the zlib can compress more. But zstandard, once again, much faster. And then if you look at the final output size, zstandard is much, about half the size of the zlib. So you get better compression much faster if you use zstandard and you combine it with quantization. Okay, so quantization is not a filter. We tried this with a filter, but the problem is when you apply it, that's no problem, but when you're reading it, you don't need to do anything. You've already zeroed out your bits. There's nothing to be done by the reading filter, and yet readers still needed to have the filter installed in order to read the data, right? There's no way to do a write-only filter that is not needed at read time. Oh, well, we should have tried that, but we didn't. But also there was a performance problem, which is you're going through your data in extra time, right? But you still need to have the filter, right? It doesn't do anything. Let's talk later. Okay. Okay, so instead we inserted this code in the heart of NetCDF where we do our translation of types and checking of values anyway, so it's no extra work. And it's fully backward compatible, even with older versions of NetCDF. So we're just changing the data as we write it, so therefore the user does not have to see anything or do anything special to read it. So should you guys have some kind of quantization? Maybe, filter or some other way, think it over. I have found that with atmospheric scientists, they seem to welcome the separation of lossiness from compression because they get to specify a number of significant digits, which they totally get and understand. Whereas with lossy compression, it's a little harder to say, you know, what's happening there, right? So anyway, it's very popular at NOAA. We're going to use it in, I think, most projects. Okay, here's an existing project around filters, and it was where we did the work that ended up being in NetCDF now. And this project is not over. It's called the Community Codec Repository. And the idea of this project is to gather together a curated set of HDF5 filters for the NetCDF community and give them one install package that can do all of the filter installs they need. And when we did this with zstandard, we got such great performance that we were able to convince the NetCDF team to just put zstandard right into NetCDF so everyone can use it. But we still intend to use this to try out other compression technologies. And here's another one that we just started, in case anyone's interested in collaborating. Measuring the I/O on high-performance computing systems is obviously a whole art in and of itself. And so what NOAA wants is a way to do it that kind of represents the way NOAA reads and writes data very exactly, so that we can get benchmarks on a machine that will tell us exactly what our software is going to do. And that's what this project is going to achieve. So if anyone's interested in benchmarking kind of model data on high performance computing with compression, please get in touch with me. And that's all I have. This is a picture from yesterday of the island of Crete from the Sentinel-3A Olchi instrument. Beautiful, a beautiful instrument. Any questions? Okay.
Thanks for your talk. I'm a bit surprised because I've investigated exactly this 5 years ago, and I'm just looking back at my data. Well, I implemented quantization exactly the same way you did. It's easier to implement than to pronounce it. And I coupled it with Bitshuffle LZ4 because that's the algorithm that we are mostly using. And I found absolutely no synergetic effect by removing bits of the mantissa. I I got exactly what was expected as minimum enhancement of the compression ratio. That means that if I remove 1 bit, I save, let's say, 1/32 of the data. If I remove 10 bit, and so on. So I get a perfect linear correlation between the number of bits I remove from the Mantissa and what I got as compression ratio. Do you believe that the better results you obtain are due to this standard, or?
Yes, I believe zstandard has got more sophisticated algorithm development and is faster, and it gives you better results, at least. That's my
Well,
only
faster than
explanation.
LZ4 now, but
That's my only explanation. Yeah.
Okay.
Anyway, it's there. Test it and see how it works for you.
but it's working. But I didn't get any enhancement, let's say.
Have you tried the NetCDF?
No, not yet, because I'm just discovering it.
Yeah. Well, let me know if it doesn't help.
So the question back here first, I think.
If you're getting big blocks of zeros after you do your quantization, do you also shuffle?
Yes, shuffle works well and adds to it. And I should have put the graph in that included that. Yeah.
So I think you were first.
I'm just wondering, have you compared it with ZFP from Livermore? Because they do kind of the same. User can specify a number of digits to preserve, and then compression works. And ZFP is now working on GPUs.
Oh, that is a great tip, and I will look at that. The difficulty in picking a compression method was finding one that the Unidata team felt was universal enough that every single NetCDF user could easily get access to it. And zstandard was the one that seems to have the greatest penetration of all in terms of different platforms and operating systems. So that's what we went with. But I think if we can find more and others, that the case can be made that they also should be fully supported.
In the last comment, I realized what you were saying, that the filter should be present, but this is something we should look in the file format, because now we're using only 2 flags, this mandatory. There can be more flags that then filter can use to bypass, right? It will be very easy to implement, because we just need to introduce, and then it can be programmed.
I can imagine you would want to have filters that you only use at read time and
Right,
others that you only use
right.
at write time.
I was curious, like, how does quantization compare to the scale offset filter, which is part of the standard HDF5 library?
It's not as good because I tried scale offset. The compression rate is great for scale offset. One of the problem is that you end up by storing data which on blocks that are not multiple of 8 bits. That makes the compression later on more difficult. But because you're storing integers, and with quantization, you keep a mantissa that is still mainly noise, let's say it. The mantissa itself doesn't compress well. So scale offset works better.
So any other questions or comments? Okay, yeah. Okay, okay.
I was actually curious if the data on which you are benchmarking this are somehow specific, or how they look like. Like I can imagine like very large and same values, or how much they oscillate. Are they close to integers?
It's atmospheric science data. So data from a model. So mostly it would be fields that are not continuous, but slightly varying across the geographic regions, like a temperature. So they would have relationship to each other, which makes them easier to compress, right? If we just put in a bunch of totally random data, then they really wouldn't compress at all, right? If you put in data that's extremely regular, then it compresses really well. So this is somewhere in between, and it's meant to model atmospheric data.
Okay, thank you.
Sure.
So thanks. Any other questions? If not, I guess we can say thank you again.